In physics, mass is a property of a physical body. It is a measure of an object's resistance to acceleration when a force is applied. It also determines the strength of its mutual gravitational attraction to other bodies. In the theory of relativity, a related concept is the mass-energy content of a system. The SI unit of mass is the kilogram. Mass is not the same as weight, even though we often calculate an object's mass by measuring its weight with a spring scale, rather than comparing it directly with known masses. An object on the moon would weigh less than it does on Earth because of the lower gravity, but it would still have the same mass. This is because weight is a force, while mass is the property that determines the strength of this force. In Newtonian physics, mass can be generalized as the amount of matter in an object. However, at very high speeds, special relativity postulates that energy is an additional source of mass. Thus, any stationary body having mass has an equivalent amount of energy, and all forms of energy resist acceleration by a force and have gravitational attraction. In addition, matter is a loosely defined term in science, and thus cannot be precisely measured. There are several distinct phenomena which can be used to measure mass, although some theorists have speculated that some of these phenomena could be independent of each other. Current experiments have found no difference in results, whatever way is used to measure mass. Inertial mass measures an object's resistance to being accelerated by a force. Active gravitational mass measures the gravitational force exerted by an object. Passive gravitational mass measures the gravitational force exerted on an object in a known gravitational field. Mass energy measures the total amount of energy contained within a body, using E equals mc2. The mass of an object determines its acceleration in the presence of an applied force. The inverse relationship between mass and acceleration is called inertia. According to Newton's second law of motion, if a body of fixed mass m is subjected to a single force F, its acceleration a is given by F per meter. A body's mass also determines the degree to which it generates or is affected by a gravitational field. If a first body of mass m is placed at a distance r from a second body of mass mb, each body is subject to an attractive force Fg equals gmamb r2, where g equals 6 quintillion 989 quadrillion 667 trillion spade suit 6.67 times 10⁻11 n kg 2 square meters is the universal gravitational constant. This is sometimes referred to as gravitational mass. Repeated experiments since the 17th century have demonstrated that inertial and gravitational mass are identical. Since 1915, this observation has been entailed a priori in the equivalence principle of general relativity. Units of mass. The standard international system of units unit of mass is the kilogram. The kilogram is 1,000 grams, first defined in 1795 as 1 cubic decimeter of water at the melting point of ice. Then in 1889, the kilogram was redefined as the mass of the international prototype kilogram, and as such is independent of the meter, or the properties of water. As of January 2013, there are several proposals for redefining the kilogram yet again, including a proposal for defining it in terms of the Planck constant. Other units are accepted for use in SI. The ton is equal to 1,000 kg. The electron volt is a unit of energy, but because of the mass-energy equivalence it can easily be converted to a unit of mass, and is often used like one. In this context, the mass has units of C2. The electron volt and its multiples, such as the MeV, are commonly used in particle physics. The atomic mass unit is 1/12 of the mass of a carbon-12 atom, approximately 6 quintillion 973 quadrillion 166 trillion spade suit 1.66 times 10⁻27 kg. The atomic atomic mass unit is convenient for expressing the masses of atoms and molecules. Outside the SI system, other units of mass include: the slug is an imperial unit of mass. The pound is a unit of both mass and force, used mainly in the United States. In scientific contexts where pound and pound need to be distinguished, SI units are usually used instead. The Planck mass is the maximum mass of point particles. It is used in particle physics. The solar mass is defined as the mass of the Sun. It is primarily used in astronomy to compare large masses such as stars or galaxies. The mass of a very small particle may be identified by its inverse Compton wavelength. The mass of a very large star or black hole may be identified with its Schwarzschild radius. Atomic mass. Typically, the mass of objects is measured in relation to that of the kilogram, which is defined as the mass of the international prototype kilogram. A platinum alloy cylinder stored in an environmentally monitored safe secured in a vault at the International Bureau of Weights and Measures in France. However, the IPK is not convenient for measuring the masses of atoms and particles of similar scale, as it contains trillions of atoms, and has most certainly lost or gained a little mass over time despite the best efforts to prevent this. It is much easier to precisely compare an atom's mass to that of another atom, thus scientists develop the atomic mass unit. By definition, 1U is exactly 1/12 of the mass of a carbon-12 atom, and by extension a carbon-12 atom has a mass of exactly 12U. This definition, however, might be changed by the proposed redefinition of SI base units, which will leave the Dalton very close to 1, but no longer exactly equal to